Alright, before we start, I'll recommend you to watch these videos first. If you're done, let's get into it. We recall that all differential form of electric and magnetic field we derive until now, which these three has universality, of course in both divergence here and the curl here relate to Faraday-Lenz law. And now we'll define potential for electric and magnetic field such V and A here, that this addition related to new curl here, that if we plug in electric field here, we will get the consistent to the vector potential definition here, which curl we know it delayed the non-solenoid vector field such nabla V here, and by plugging the A here to the Gauss law for electrostatic, we have a problem with A, so we choose nabla.A is equals to 0, which will be our little discussion in this video. So by new definition of potentials, we will get this Poisson equation for V and A vector field here. And the question is, why we choose nabla.A is equals to 0? Or for more fundamental, what is V and A talking about? In previous video, we defined V and A as electromagnetic potentials. As before, if we choose nabla.A is equals to 0, then we will have V as this integral, which A is some point, and A vector here related to this integral, so it consistent to our magnetic field and electric field definitions. So then, if we transform A to the A prime like this transformation, which lambda here is scalar function depend on position only, then the magnetic field will remain the same. So by this result, we can choose nabla.A is equals to 0 as before, and this thing related to gauge fixing, which will be our discussion in other videos. Next, we recall definition of work as this integral. So in electrostatic case, which magnetic field is equals to 0, work is equals to this integral due to Lorentz force definition. And then Q here is a distribution along R, so we can put Q outside of the integral, and this integral is definition for potential as before. So here, if we take one by one for many particles and then we extend to continuous, then we will get this summation here, which Vig here relate to potential from other than Qi, which means that if only Qi alone, there is no work. And if there is another Q, let's say Qj, then work is non-zero as potential from other than Qi exists. And for continuous distribution, we will get that the partition of work is equals to potential multiplied by partition of charge. So then if we take the integration for both sides here and we change variable with region of volume, then this part tells us about charge density. And here if we take the substitution to for other side in region omega, then it will relate to energy density for electric field as UA in region omega. So by this integral, we will get this by using Gauss law for electrostatic, and this integral will become as this by product rule. So we get this part is equals to minus E for electrostatic, and here we can switch to counter surface integral by divergence theorem. And whoopsie, I forgot to add epsilon 0 here. Here's the crucial. If we take omega along entire space, then surface A here is surface at the end of space. So by energy conservation, that no energy go out. So to guarantee that, we took surface counter integral here equals to 0, which to maintain the consistency of no energy go out. But here, UA need to redefine as double UA. Why? Because UA before tell us one by one charge energy effect. But by definition of work here, work only exists if there is an interaction, which A tell interaction between two charges. So here we need to redefine by two factor because of energy between two charge similar amount to one charge. So here, UE after will be UE is equals to 1/2 multiplied by V rho, and then UE equals to epsilon over 2 multiplied by E dot E here. This thing related to energy density of electric field, not the electric charge. And next, we back to the definition of W. Here, we can substitute the variable of integration as velocity like this. So for partition dq, the partition of W is this equation, which here, if we take the energy density, let's say omega, then omega will equals to this. And by taking first derivative of omega with respect to t will equals to this, and this is related to power density. And here, because of electric current density, the definition of E will become as this. And here, I will separate nabla V dot J as omega 1 and the other one is omega 2. And here, omega 1 by integration with T and volume, it will bring us to UE as before. So here, we will focus on omega 2. Here, A is time dependent because of partial differentiation, and J here may be time dependent because of Ampere law. And here, if we stop to magnetostatic field, then B must be time independent. This looks like inconsistent. So here's the trick. We separate A and J by variable separation as this. We separate space and time by some function. So here, we will get the Ampere law equation for magnetostatic as this. That's what we're looking for magnetostatic. So the omega 2 will become as this. And by integrating with volume, we will get power of magnetic potential as this. And integral again by t, we will get as this. And notice that here, the interval of integration, lower bound of interval, we need initial condition, and the upper bound here will relate to magnetostatic condition. So the initial we took value as 0, which no current, and magnetostatic here, the current is constant as J vector field, which here lambda is equals to 1. So the result of integration will have at this interval, and the final result of W here will relate as this. After that, we use Ampere law to determine J here, and the next one we use product rule, so we get this, and by potential definition and divergence theorem we will get as this. And here, by energy conservation, we will take the counter integral here is equals to 0. So that means the result here we can define as UB as energy density of magnetic field, especially for magnetostatic field. And for summary, we get new thing about electromagnetic potentials, which we can choose catch fixing. For example, nabla dot A is equals to 0, and then we will get this integration for both electrostatic and magnetostatic field, which by this we will get the energy density definition as this, which we only take the special case for electrostatic and magnetostatic, which obviously will be our questions that what for accelerated charged particle, which no more electrostatic and no more magnetostatic conditions. This will be our discussion in next videos. Thanks for watching this video. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If there is any questions, please drop comment below, and see you later.